to see the first of Maxwell equations written in the differential form as Maxwell wrote. So, in the previous video we saw that the divergence of the electric field is equal to the total charge density divided by epsilon naught. This could be divided into the free charge density minus the polarized charge density. With the polarized charge density could also be written as the divergence of the electric dipole moment per volume. So the charge density, this is the free charge density, so all this divided by epsilon naught. The free charge density divided by epsilon naught is equal to the divergence of the electric field plus the polarized the electric dipole moment divided by volume divided by epsilon naught. So this was the first of the electrostatic equation for the dielectrics. In the days of Maxwell, it wasn't known this charge density, so it was thinking more as some constant d. Well, d is a linear combination of the electric dipole moment and the electric field. Electric field, here we would have times epsilon naught. So if we divide everything here by epsilon naught, we have E plus the electric dipole moment per volume divided by epsilon naught. That is exactly what we have here. So we have that the free charge density divided by epsilon naught is equal to the divergence of d divided by epsilon naught. We can multiply everything by epsilon naught, and we have that the charge free density is equal to the divergence of d, and this is the way that the first Maxwell equation was written, and this is the first equation that I have here. The other thing is that then we can put P would be equal to D minus epsilon naught times the electric field. Also this electric dipole moment per volume, we saw that it is C times epsilon naught times E. So D actually could be the electric field multiplied by the electric field times C times epsilon naught plus epsilon naught times E. So this is E times epsilon naught times 1 plus X, and this is the K constant, or the electric constant. So we have that D is equal to E times epsilon naught divided times K, and this is a constant specifically for each dielectric that is called epsilon without the naught. This is the permeability of the vacuum space. This would be just the permeability, and so we have that D is equal to the electric field times epsilon. But this is not true whenever the electric field becomes very, very large, because whenever these two become very large, the proportionality does not hold. And the last thing in the previous video that we mentioned, that the circulation or the curve of the electric field before the electric is equal to 0, and after the dielectric was put is also 0. So because these two things are the same and the curve of this is the same as the curve of this, that means that the electric field before the electric and the new electric field So, well, this is the new electric field, and the new electric cadence, the new electric field, is the electric field divided by the constant K. So the electric field, the new electric field after the dielectric is put on the capacitor, is actually the electric field before the capacitor decreased by a factor of K.